Now we have to evaluate the integral given by root of x upon root of x plus root of 9 minus x from 0 to 9. Now here we try to guess like which property seems to be useful here. If you observe, the addition of limits 0 plus 9 gives us 9, and we remember the property that the variable x can be replaced with a plus b minus x, isn't it? In that case the function remains same. So in our case we can replace x with 0 plus 9 minus x. So that is nothing but x can be replaced with 9 minus x wherever we see. So in this case, without changing the limits, the x in the numerator will get changed to 9 minus x. Similarly, in the denominator, x becomes 9 minus x plus root of, here we already have 9 minus x. So in place of x, we must write 9 minus x dx. So now if you see, this gives us 0 to 9 root of 9 minus x upon root of 9 minus x plus, in the second root we get simply x because 9 gets cancelled, dx. Now we have to follow a specific trick here, that is, let us denote the original integral as say I. If we compare the two expressions that we have got, that is the two functions, basically both are the same integrals I, isn't it? Now let's see what happens if we add the two integrals. Now since the limits are same, we can definitely add the two functions. So on adding these two, we will see that since the denominator of both expressions are same, we can add the numerators. So in the numerator we have root x plus root 9 minus x. So ultimately we get numerator same as denominator, which is nothing but 1. So we have to basically evaluate the integral of just 1, which is nothing but x, and evaluated from 0 to 9. It's 9. So that gives us 9 minus 0, which is nothing but just 9. Now this is equal to twice the integral. So therefore the value of the integral is nothing but 9 by 2, which is the final answer. So you see how the use of property simplifies the question to a great extent. Let's go ahead and see another question. Now here we have to evaluate the integral from 0 to infinity of log x upon 1 plus x square. Now here remember that infinity is just there kept as a upper limit. It is actually not to be considered as a specific number, right? Now looking at the expression, we see that where does infinity come into picture? That is when we consider tan of pi by 2. That is, although technically we say that tan of pi by 2 does not exist, but it actually approaches infinity, right? So that means as the angle becomes closer to pi by 2, the tan of that angle approaches infinity. So with this in mind, we also observe that we are having the pattern that 1 upon x square plus 1. So where does 1 upon x square plus 1 come into picture? So we see that this is the derivative of tan inverse of x, isn't it? So that gives us some clue to try out. So let us do the substitution of tan inverse of x by t. Okay. So if that is the case, on differentiation we get 1 upon 1 plus x square dx is equal to dt. Now we have to also replace x in the log x, correct? So if tan inverse of x is t, then obviously x is nothing but tan of t, right? Now next we have to also change the limits. So that is when x is 0, what will be t? T is tan inverse of x, so tan inverse of 0 is also 0. And when x is infinity, that means t is theoretically equal to pi by 2, right? So this is how we remove the infinity in the substituted integral. So now therefore our integral equals integral 0 to pi by 2 log of x is nothing but tan t. So here we have log of tan t, and dx upon 1 plus x square is nothing but dt, right? So now we have to evaluate this. Now let us again take advantage that we have 0 and pi by 2 as the limit, so their sum is pi by 2, and we have the trigonometric quantity tan. So if we replace the variable t with lower limit plus upper limit minus the variable, so that is nothing but if we replace t with pi by 2 minus t, the value of the integral will not change. So therefore we have 0 to pi by 2 log of tan of, in place of t we have to write pi by 2 minus t dt. Now we know that tan of pi by 2 minus t is nothing but cot t, so that is basically cot t dt. So this is also I, isn't it? If we call the previous statement as 1 and this new statement as 2, suppose we add 1 and 2, which gives us 2i equal to integral of, now when you add we have log of tan t plus log of cot t. So using the rules of logarithms, that equals log of tan t into log of cot t, since the limits are same, 0 to pi by 2. So that gives us integral of 0 to pi by 2. Now tan t into cot t is equal to 1, right? And we know that log of 1 is 0 to any base. So therefore ultimately we have the answer as 0 because there is nothing to integrate here. And since the value of 2i is 0, that automatically gives us the original integral also is equal to nothing other than 0. So that's how we use the substitution method and the properties to solve this question. Let's see a couple of more questions. Now here we have to evaluate integral of sine square x from minus pi by 4 to pi by 4. Now if you observe, this gives us a clue that is integral is of the form minus a to a, and which is that property which comes closer to this question is, if you remember, in this type of integral, if we can check whether f of x is an even function or odd function, then that can be simplified using the property. Now if you see our function is sine square x, so even if we replace x with minus x, since the sine of minus x is ultimately getting squared, it will be same as the sine square x only. So therefore yes, we have an even function here. So using the property we can say that this integral is equal to 2 times integral from 0 to pi by 4. Yeah, here we have 0 to pi by 4 sine square x dx. Now the next question is how to evaluate this. For that we use our normal method of integration, that is, first we try to evaluate using the indefinite integral and then substitute the limits because that is the simplest way. Sine square x we write as 1 minus cos 2x upon 2 times dx. Now the 2 will get cancelled and the remaining expression is very easy to integrate because integral of 1 is x and integral of cos 2x is sin 2x upon 2, and this is integrated from 0 to pi by 4. So putting the upper limit we have pi by 4 minus sine of 2 into pi by 4 is sine of pi by 2, which is sine 90, which is 1. So we have 1 by 2 as the expression of upper limit minus, when we put x as 0, first term is 0 minus sine of 2 into 0 is sine 0, so which is finally 0. So therefore the final answer is pi by 4 minus 1 by 2. If you want, we can simplify it as pi minus 2 upon 4. Let's see one more question. Now here we have to evaluate the integral of cos x upon x cube plus x from the limits minus 1 to 1. So here once again we see the limits are of the form minus a to a. So we can bank on the property where we need to check if f of x is even or odd. Now what happens if we replace x with minus x? We will get cos of minus x upon minus x the whole cube plus minus x. This gives us, we know that cos of minus x is same as cos x because cos is an even function. But in the denominator, since we have odd powers of the variable, we get minus x cube minus x. So taking minus sign common, we realize that we get the original function inside the bracket. So that means the given function is an odd function. So therefore, with the help of property, we can directly write the answer as 0. Right? So we have here used the property relating to odd function.